Hello, welcome back to Engineering 201 Electrical Fundamentals, and I wanted to pick up where we left off last time talking about inductors, their characteristics and whatnot. We had dealt with voltage, current, power, and energy, but we hadn't talked about series and parallel combinations and things like that. The other thing that we did mention, but is really important, is to remember that an inductor, as you make an inductor, you're coiling something up around a core, whether that core is an iron core, an air core, whatever that might be. As you coil that up, you're also adding a tremendous amount of resistance. So while you have inductance, we shouldn't necessarily think of an inductor just as solely an inductor. You usually are going to have it being in addition to a resistor. Sometimes R sub L is the internal resistance of that inductor. So that's something always to think about. Next term, when we get into AC work, we're going to do some experiments dealing with this, and we'll find out the resistive portion might be twice or three times that of the inductive portion. So it can have a big effect on the circuit. Well, the thing that I wanted to do next as we moved on was to talk about a series combination of inductors, and your author in the textbook goes through the derivation. I'm just going to come to the conclusion, and that is, could we convert inductors that are in series to one single inductor? So one single inductor like this are equivalent, and we could, of course, and that would simply be equal to L1 plus L2 plus L3 plus, we'll do this real math-like, Ln. You simply add those up. And then in parallel, and again, your author goes through the derivation of this in the reading. You can look at it if you want to, but we could reduce this parallel combination to one single inductor. I think I said resistor before. I better go back and correct that. Sorry about that. Backing up here. Didn't start out the lecture well. So we would have a equivalent inductance. Okay. Now you're probably going to have some resistance with each of these, and you could sum up that resistance too. I'm not going to try and hide my mistake with that, but that would be something probably to think about. But with these inductors here, this would be the equivalent inductance, not the equivalent resistance. So now if I look at the equivalent inductance here, that's going to be equal to, we'll do this just like we do resistors, that's going to be 1 over L1 plus 1 over L2 plus 1 over L3 plus 1 over Ln, or the inverse of the sum of the inverses. So in short, we could say, and maybe this is why I had resistors on the mind, is that this is the same as a resistor. So inductors and resistors are the same. Put that in quotes. They're certainly not the same, but we handle them the same. We add them up in series the same. We simply add them. We combine them in parallel the same. We sum up the inverses and invert that. And then, of course, the caveat to this, and capacitors are opposite. Okay, so we handle capacitors in parallel. This way over here, we just simply add them up, whereas capacitors in series, if you'll remember, we had to combine them this way. So as we walk away from this, remember that we combine inductors and resistors the same way, and capacitors are kind of the odd one, the different one, if you will. Well, I've got a couple of things that I'd like to finish up with before we significantly change gears and start to look at transient circuits. This will probably be a little bit shorter lecture. I think we had a longer lecture, the last one. We'll get finished up with this, and that'll put us at a very nice stopping point, and we'll talk about what we've got left for the term at that point. So with that, again, I mean, we could go through some examples here, and maybe this is worth talking about. Maybe we'll put a clean sheet of paper here. So if we start thinking about preparing for the final examination, what we could do now is we could take some boxes like this. This is always a great test question because you can draw this out once. And you put 1 and 2 and 3 and 4 in here. And you say if each one of those was a 1 k ohm resistor, what would this be over here? Or if each one of these was a 1 millifarad capacitor, what would this be? Or if each one of these boxes contained a 100 millihenry inductor or something like that, what would this be? So you'll definitely see a question like this on the final. And again, what led me into this was you'll handle this exactly the same for resistors and inductors, and then capacitors are going to be the odd one. So you've got some homework problems. I'm not going to belabor this that test you on this, but this is a heads up on a final question, I guess a bonus for people that actually watch this video. See something like this on the final, and it's a great question because with one diagram we can get 3 questions out of it. What if each of these is a certain capacitor? What if each of them is a certain resistor? What if each of them is a certain inductor? And this might have different geometry. I mean, we could make this more fun if we wanted to bring this over here like this, but that's the game plan. So practice again. If you struggled with equivalent resistance, make sure that you go back and work on that, and also concentrate on equivalent inductance and equivalent capacitance. Well, let me get back to this one then. So looking at this, I've got the operational amplifier here. So we're going to go back and we're going to take our work that we previously did with the operational amplifier, and we're going to combine a capacitor in here. So stepping back in a couple ways, going back to capacitors, going back to operational amplifiers. And what I'd like to do is with this come up with the output voltage here. So I'm going to assume linear operation. So with linear operation, I know that this current here, I minus, and this current here, I plus, I minus equals I plus, has to be equal to 0. And then I know that the voltage V1 is equal to, and I might be better off to draw these as time varying. So yeah, I'll do this. V1 is equal to V2, and like I said, probably should write these as time varying, that V1 is equal to V2, lowercase, and maybe even, I don't want to have to change these I's here, but you could make a note here that these are probably some function of time, although if they're equal to 0, that's not a very interesting function of time. So with that, we're going to tackle this problem exactly the way that we have always done problems in the past. I'm going to look at some currents. So I could talk about, maybe I'll talk about I1 here, and I could talk about I2 there, and I could say that I1 plus I2 plus I minus, those two are going in. I guess technically you'd say that this would be a negative I minus, since it's leaving, but it's going to turn to 0 anyway. So that's equal to 0. So we recognize then that this goes to 0, and we have then I1 plus I2 is equal to 0. So let's talk a little bit about I1. Remember, the governing equation for a capacitor is that I is equal to C times dV dt, right? So I can say then with I1 that I have C1, that's the value of the capacitor, times the derivative of some voltage with respect to time. And what's that voltage going to be? Well, again, if the current is going to the right, I need to look at the voltage there, which is going to be minus V1 plus Vs. So minus V1 plus Vs. Okay? And then I2, that's just a good old Ohm's law. So I'm going to have to find the voltage like that, which is going to be minus V1 plus V0 divided by R2, right? And that's equal to 0. Now, V1 is equal to V2. What is V2 equal to? Well, V2 is equal to 0, therefore, in this case, and this isn't always the case, we know these are equal. Sometimes they're equal to 0, sometimes they're not. Well, if V2 is equal to 0, we know that V1 has to be equal to 0. So I've got 0 there, and I have 0 there. So I can say then that V0 is equal to, let's see, if I move this over there, I get a negative, so I'm going to have minus R2 times C1 times the derivative of Vs dt. Or maybe I should emphasize these time-varying functions and say that V0 as a time-varying function, V0 of t, is equal to minus R2 times C1 times the derivative of the input voltage, which is going to probably be some signal, dt. Okay, we double check that. Minus R2, C1, yeah. So that would be our conclusion here. And we look at what this does, and if I have the input signal, this is what's going in. What's it doing to that? It's actually differentiating it, isn't it? So we could say that the output, our output, which is equal to V0 t, is actually proportional to the derivative of the input. Okay? So our output is proportional to the derivative of the input. So what do we have here? We have a differentiator, don't we? Okay? So we've actually made an analog computer that differentiates. We the past ones, we had inverters and we had non-inverters. They'd multiply by a positive number, they'd multiply by a negative number. We essentially made analog computers that would multiply. Here we've made one that will differentiate. And this could be good for a simple task. I think a lot of you are in physics class, and you remember that if you have the position of something, you could differentiate that to get velocity. Or if you have the velocity, you could differentiate that to get the acceleration. So maybe you're making a measurement and it's convenient to measure one quantity and you want to record another quantity. You can put one of these on your measurement equipment and differentiate that signal. So pretty handy, actually. Well, let's do one more. And I think you've got some homework problems like these that will give you a chance to try this on your own. So we'll come over here and we'll look at this. We take our capacitor and our resistor and we change places with it. And we'd like to then come up with what our output voltage is here. So again, I'm going to assume linear operation. And maybe this one I'll be a little more careful on my characters here. I'm going to say that this is I2, and I'll say that this is, no, I wasn't careful enough. This should be I positive, not I2. And this will be I minus, won't it? And then we would have V2 here, and V1 like that. So I could say with linear operation that I minus is equal to I plus is equal to 0, and that V2 is equal to V1. Okay. Well, we'll do this like we've done many times before. I1, and what do we have here? I2. So we could say that I1 plus I2, let's see, those are going in, so then subtract I minus is equal to 0. Of course, know that that's equal to 0. And I can say then that I1, what do I get for I1? I need to find the voltage that's going like that, right? So that's going to be minus V1 plus Vs divided by R1 plus I2. What's I2? Remember our equation, governing equation, that I is equal to C dV dt, right? So let's use that. So I'm going to have C2 times the derivative with respect to time of what? Current's going that way, so I need to find the voltage going that way. Minus V1 plus V0. Minus V1 plus V0. That's equal to 0. Nice equation. But what? Two unknowns. Well, I come back over here, V2 is equal to 0 volts. Okay, even if there was a resistor in there, because this is equal to 0, V2 has to be equal to 0. So therefore, V1 is equal to 0. So if I get to say that that's 0 and that's 0, I now have an equation that I can solve for V naught, the output, in terms of V, let's see, I think I've got a mistake here. So when I did this, so I1, I was going from there to there. So that means I went minus V1. I like that. And then I had to go back up over here, which is what? Vs, isn't it? Vs. So this should not be V2, but rather Vs. Now are we okay? I want to try and find the voltage from this point to that point. So I go minus V1, because V1 by definition is that. So minus V1 gets me down here, and then Vs gets me back up there. Let me double check the voltage across this. I'm trying to go from there to there, right? So if I go from there to there, that's minus V1. And then back up here from the ground state, that's by definition V0. Good. I think we're okay with that. So now I'm going to have to, as I could rearrange this a little bit and say that I had could move this to the other side. Then I'd get a negative sign. So tidying this up a little bit, I have 1 divided by minus R1 times C2 times Vs is equal to, this would have gone to the other side, the derivative of V0 t. Does that make sense? I move that to the other side, I get a negative, so then I'm going to divide both sides by minus C2. Vs comes from over there, yeah. So I got that set up because now my unknown, this is what I'm looking for, is in the argument of the derivative, so I'm going to have to integrate this thing, right? So I could say that V0, maybe we'll say, make sure we know it's a function of time, is equal to minus 1 over R1 C2. We're going to assume that those are constants, times the integral of from x equals minus infinity to x equals t of Vs of x dx. And a lot of times they'll just say V of t dt. You could, depending on how you want to think about that. I could break up this integral if I wanted to. So come over here. V0 t would be equal to minus 1 over R1 times C2 times the integral. I'm going to break it up and say it goes from 0 to t. 0 to t of Vs of x dx. And then I'm going to have V0 at t equals 0, indicating the initial charge. because I took the integral from minus infinity to 0. That's what this is. The integral from minus infinity to 0. And furthermore, I'm going to say that this to keep life easy for us and say that this is equal to 0, has no initial charge. Okay, we'll just say that. If it had some initial charge, you'd want to put that factor in there, but usually we don't have to worry about that. So I can say then that V naught T is equal to, cleaning this up, minus 1 over R1 C2 times the integral from 0 to T of Vs of x dx. Okay, and that says, of course, x is equal to t and x is equal to 0. Sometimes people will just say from 0 to t and then put Vs t dt. That's a little bit confusing then, because then you're saying that, well, t is equal to t for your limits of integration. But that's a good result, because in the end we get what? We get that our output is equal to, maybe I won't say equal to, I don't want to have to worry about this factor up here. I will say proportional to the integral of the input, right? Okay, so what is this thing? This is an integrator. Okay, an integrator. And speaking of your work in physics, measuring acceleration is actually very easy to do. You can get an accelerometer very inexpensively. Sometimes even with important equipment, they'll pack an accelerometer with it so that you can tell when and if it was damaged in shipping, who's going to be responsible for that. And the interesting thing is, if we get acceleration data, if we were to integrate that, we could get velocity data, couldn't we? And if we integrated it further, we could get position data. And in dynamics, we'll even talk about, if we carefully keep track of our acceleration, we could figure out where we were. That's the principle of inertial navigation. So having circuits that can do integration, that can do differentiation, those are important. Well, we get to an interesting point here. I've finished up a few kind of eclectic things. Before we move on, we have two big sections left this term. One section is transient analysis. What happens if I have a circuit and maybe I have a switch in it, and I move that switch and the capacitor starts to either charge or discharge, and an inductor starts to behave differently or something like that. We're going to look at resistors and inductors and resistors and capacitors. And that's going to require us to talk a little bit about differential equations, and then try and quickly put that into a very piecewise six-step method. So that's where we will go next. Then the only remaining section before there in the end of the term is to talk about an introduction to AC analysis, which is essentially going to be an introduction to all of next term, which should be good. Our civil engineers that are only going to be with us maybe this term, it's good that they have a quick introduction to AC, and for everyone else it'll be good to prime the pump for next term. So that's what we will do. We'll next time we'll get together and talk about transient circuits. Those are going to be good circuits for us, because a lot like the maximum power problems, they require us to do quite a bit of circuit simplification, so they come at a good point in the term as we're trying to review and get ready for wrapping this term up, doing a final and things like that. So thank you for watching, and take care till then.